Good morning, stats. This is the video for the 11.2 extra examples, the chi-squared test examples. We're going to get cracking on it right away. This is your assignment for the day. Let's go. Every year, Ms. Gallus surveys a random sample of 50 seniors at her large high school to find out what career they intend to pursue after high school. She wonders if the distribution of intended career choices has changed in the last 5 years. The two-way table summarizes the data from the two samples, and they give you the graduating class 2012 to 2017, some different types of careers, and it asks you to state some hypotheses. So the first one, state the appropriate hypotheses and null hypotheses, appropriate null and alternative hypotheses for the two problems. So this problem is asking, as time progresses, is there a change in career choices? So our null hypotheses would be there is no change, and our alternative hypotheses would be that there is a difference. So H of O, there is no difference from 2012 to 2017 in career choices. And my alternative hypotheses would state there is a difference from 2012 to 2017 in career choices. Okay. Show how the calculation for the expected count in the arts and humanities cell then provide a table of expected counts. Well, I'm going to show you that just by coming up here. And we're gonna make an expected counts table. Is what we're going to do. We're just gonna go through and we're gonna make a table that says expected. And that's really what we do here. So that after, if we have this expected counts table, it makes it really easy to find our chi-squared test statistics. So here's our expected counts table. And it's going to look very similar to this one. I'm going to paraphrase some of it. I'm not going to write out all the numbers here, but I'm just going to go arts and humanities. I'm going to go social sciences. I'm going to go STEM. Woohoo, go STEM. I'm going to go other / undecided. And then I have my totals here. Okay? And for these chi-squared values, when you have two-way tables, your expected counts are gotten right off of these charts. And really you have to have these total columns because the calculation is very easy. You take row total times column total divided by chart total. So for this cell right here, row total 32 times column total 50 divided by table total 100. So I'm going to do that right now. I'm going to go 32 times 50, enter, divided by 100, enter, and I got 16 for that cell. And if you have this in table format, it makes it really easy because then I can do observed minus expected divided by I can go 22 minus 16 squared. All over 16 squared, and the chi-squared test statistic just falls right into place. It does take a little bit of calculations, but it falls into place. But that's it. Let's. It wanted. Let me see here. It wanted the calculation for arts and humanities in 2012. So that's my arts and humanities in 2012. That's it. Row total 32, column total 50, and then you divide it by that 100. So what you need to do right now is you need to go and fill in these boxes right here to finish the problem off. To show it, it said to show it on that problem, I'm going to do 32 times 50 all over 100. And it's that easy. You guys can hit pause and you can go find those numbers. Okay, now on the bottom one, letter C, it says find the value, calculate the value of the chi-squared test statistic. It's going to take a little bit. Chi-squared, I'm going to get you part way there. Chi-squared, it's observed. Observed minus expected squared over expected squared. So that one is 22. Observed in the first cell, 22 minus 16 squared all over 16. Plus the next cell over, I have 10. 10 minus the expected in that, you should have gotten 16 all over 16. Dot, dot, dot. And you're going to do that all the way down. You're going to have 1, 2, 3, 4, 5, 6, 7, 8. You're going to have 8 of those fractions. And then you can go in and you can find your chi-squared test statistic. And the answer to this problem is just that number. You don't have to go in and find a p-value. No chi-squared CDF. None of that. It's just what is the value of this chi-squared test statistic. Go ahead, go in, and you can start and you can find that. All right, next problem. In the preceding alternative example, you read about an annual survey done at a large high school to determine students' intended career choices for life after high school. Earlier, we calculated the chi-squared test statistic. So that's what you should have found when you did all of that math, when you hit pause. I hope you hit pause. Earlier we found the chi-squared test statistic. Verify the conditions are true. Random. Yep, it was random. It tells us it's an SRS. 10% rule. Okay, think about that. Well, we had, let me see here, 50 seniors. We had 50 seniors. 50 is less than 10% at a large school. So that one checks out. And now the large counts. And this large counts condition is a little bit different for the chi-squared test statistic. Our large counts is all expected have to be greater than or equal to 5. And that one checks out. You can look at your expected counts table. That's the table that you filled out. Expected counts table, everything is greater than 5. And we're already done with the first page. All right, part B on the next page. Use table C to find the p-value. Then use your calculator's CDF command. This isn't even very accurate. I'm going to be honest with you. I don't hardly ever use table C to do that. So I'm going to go in and I'm going to find it on my calculator. You do this with me. Make sure you're punching in the buttons. You'll be required to do this on your assessment in this chapter. So I'm going to go second DIS, chi-squared CDF, right there. There's my chi-squared CDF, enter. It asks for a lower value. I'm going to go 8.167. The upper value, I'm going to go for 1,000. And now I got degrees freedom. Now, when you do degrees freedom on this, there's a set formula. You do how many rows minus 1 times how many columns minus 1. And the rows, well, there were 4 rows. 1, 2, 3, 4 rows going across. So 4 minus 1 is 3. And then you do columns, 2. There's 2 columns. 2 minus 1 is 1. 3 times 1 is 3. Gives you degrees of freedom, 3. Rows minus 1 times columns minus 1 is your degrees freedom. So I have it plugged in my calculator just like that. I'll hit enter. And I got a p-value that was 0.04268. P-value. Interpret the p-value from the calculator in context. Well, just the interpret, what does it mean? Okay, assuming there was no difference. Assuming there is no difference in career choices, there is a bang right there, 0.0268 probability of probability of those differences in distribution purely by sampling variability and purely by chance. There is that probability of the given differences in career choice. I'll put that career choice. There is a 0.04268 probability of the given differences in career choice through sampling variability. What conclusion would you draw since P equal to 0.04268 is less than our standardized alpha value of 0.05? I reject H of O and accept that there is a difference in career choice from 2012 compared to 2017. And we have it. All right. Fun. Good problem. Next problem. What is your music preference? Do high school students in Michigan and California have the same music preference? We use a census at school website to select separate random samples of 100 high school students from Michigan and 100 high school students from California. Student asks, what's your favorite music genre? The two-way table summarizes their responses. Does the data provide convincing evidence at the 0.05 level? So there it is. I'm going to have to zoom out a little bit here. So there it is. And we're going to have to go through a pretty complete problem here to do this. And I'm going to get you most of the way there. All right, so state. Well, my null hypothesis, state. There is no difference difference in music preference. H of A, there is a difference in music preference. Okay, and we're going to use a alpha equals 0.05 level. And our plan, and we really right here, well, we really should decide what kind of chi-squared test. I don't think this is not a chi-squared test for goodness of fit. So it's either a chi-squared test for independence or one from homogeneity. And it says separate random samples of 100 high school students. And anytime you have separate random samples, it is a test for homogeneity. And basically what we're saying is, are the proportions in California the exact same or similar enough to the proportions in Michigan that we can say we have kind of statistical evidence that says there's not really any difference between those two. So two separate random samples, definitely a test for homogeneity. So I'm going to put, our plan is a chi-squared test for homogeneity. I hope I spelled that right. I'm a terrible speller. All right, random sample. Let's look. Yep, random sample. Check. 100 is less than 10% of all. Check. It says random. They did 100, less than 10% of all the students that check. And now the large counts. And the large counts is the first place we hit a snag. And we're going to have to go over to this do column, because what we need to do is we need to go in and we need to figure out, hey, are all of our expected counts, do we have enough? And I'm going to grab my paper here. My due step here is going to require us to make a chart. So I'm going to put Michigan here. I'm going to put California here. And we have our different categories. So there's country, pop, rap, rock, pop, rap, rock, rock, and other. Okay, and remember now, our expected counts is from the chart up above it. It's a row times column. So if I wanted this Michigan country, it'd be row times column. The row total over here, up there, row total is 16, and the column total is 100. So 16 times 100 all over the chart total, which is 200. So this first cell right here, this is 8. And what you need to do is you need to right now go in and you need to find each one of these cells so that you know if your large counts condition is met. Hit pause in a video. I'm not going to do each one of those. This is for you to do now. Hit pause in a video. Go in and find out each one of those and then answer the question, is the large counts condition met? Well, yes, the large counts condition is met. All counts are over 5 in that chart. So you should be good. And again, you need to make sure you find those in order to do this. Okay? Now, what you need to do is you're going to go in, you're going to find the chi-squared test statistic now. Okay? And the chi-squared test statistic, I got 1, 2, 3, 4, 5, and then 1, 2, there's 10 cells where you're going to do this. You're going to have 10 different calculations. So you're going to do observed, the sum of all, observed minus expected, squared all over expected. Okay, so in this case, the observed, in the first one, we had 12. Minus my expected here would be 8. And I got 12 from that chart up above. There's a little 12 in that spot, and then a minus 8. I'm going to square that, and I'm going to put that all over my expected, which is 8. Plus, if you're doing it right, that cell is going to be 4 minus 8 squared all over the expected, which is 8, plus this cell right here. What I got out of that, I got 15 minus 14.5. 15 minus 14.5 squared all over 14.5. And I keep going until I have all of them. And then I go in and I find that chi-squared test statistic. So right now you hit pause, you go find that value right now. Okay? All right, the last thing you need to do is you need to go in and you need to find your actual p-value for this so you can make your conclusion. Okay? So under the do column still, be down there a little ways, we're going to go chi-squared CDF, chi-squared CDF, and I'm going to hit mine, chi-squared CDF, and it asks you for the lower. The lower is what you got when you ran through that chi-squared test statistic. You're going to plug that in. Your upper, you can plug in 1,000. And your degrees freedom. Well, how many rows are there? 1, 2, 3, 4, 5. Your degrees freedom is 5 minus 1 times, well, columns. There's 2 columns times 2 minus 1. 4 times 1 is 4. So your degrees freedom is 4. You go in and you find that p-value there. And then after you find that p-value, you go ahead and you write your conclusion for that chi-squared test. All right? Good job. Good job. All right. We have one more problem. One more problem here. We'll do the Facebook problem, And I know there might be, I think there's maybe one other problem in this section. We're going to end with this problem right here. Here's the problem. Mark Zuckerberg, is interested in finding out if there's an association between age group and Facebook use among U.S. adults. Takes a random sample of 250 adults 18 or older and records their age and whether or not they use Facebook. The two-way table summarizes the result. Finding out if there's an association, man, that tells me right now. And two things. One, if there's one random sample, and is there an association? This is a chi-squared test for independence. Okay, that's what this is. So does the data provide evidence of an association between age group and whether or not someone uses Facebook status in the U.S.? I'm going to get you partway through this one, and then we'll go from there. Okay, so state, H of O. There is no association between age and Facebook. H of A. There is an association between age and Facebook. Press pause, make sure you have those two down. Plan right here, our plan. This is definitely a chi-squared test for independence. We're trying to see if there's an association between age and Facebook, independence, and it's called a couple different things. You can call it a chi-squared test for association or for independence, but definitely that. It tells us it's a random sample, so you can check mark the random sample box. And 250 is definitely less than 10% of all Facebook users. So you can check off the 10% rule. For the expected counts at least 5, well, we have to go in and we have to make our two-way table again. Okay, I'm going to get you started on that. So under the do column, and then you'll be able to either check it off or not check it off. Under the do column, we need a table again. So I'm going to put 18 to 29, 30 to 49, 50 to 64, and 65 plus. I'm going to put yes, and I'm going to put no. And to find each cell, it's row, which the first top row is 191, times column total, 191, times my column total, which is 68, all over the chart total, which is 250. And what I got out of that, I got 51.95. 51.95. And what you need to do is you need to go in and you need to find those cells. Go find those cells and you got it. Be done with it. All right. Large counts condition, by the way, does check out. You have to make sure you have those chart values in order to finish the problem. Okay. Next thing is our chi-squared test statistic. Chi-squared test statistic. So observed minus expected. So the observed value that I got 51. Nope, I got 60. We have 60 up in the chart minus 51.95 squared all over 51.95 plus the next cell. And just to make sure you were doing it right, I got 191. Yep, I got 64.2. So it's 64.2 minus 64. 64.2 minus 64 squared all over 64. And you're going to keep doing that until you find this chi-squared test statistic. After you do the chi-squared test statistic, you go in and you find your chi-squared CDF. Your degrees freedom, there's 2 rows, there's 4 columns. 2 minus 1 is 1, 4 minus 1 is 3, 1 times 3 is 3, so your degrees freedom is 3. You find your p-value and you conclude. You can stop after that example problem. I think you should be able to do it if you've been following along with the video. When you're done with that, you're done for the day. Good luck.